Last time that we met, we did look at how to fit multiple logistic regression, where the outcome variable is binary, and then we choose the logit link function. However, the independent variables are many and not one, like we did in the simple logistic regression model. And so we were able to get into the concepts of how do we handle multiple independent variables, some of which may be categorical in nature. For the categorical variable, we said that we should always avoid, giving them codes like numbers 1, 2, 3, but rather we should do create dummy variables to describe the relationship with the outcome. And to facilitate that easiness, most softwares would automatically convert our data into these dummy variables and fit the model with them. So the outputs that we get from our packages, you would find that there are some levels of the covariate that are assigned some effect sizes, but then one of them is set as the reference. So because of that, you will not see a coefficient that is associated with that reference. But then that makes it easy for us to do a comparison between the variable which effect is the level which effect is presented, and then the independent variable. I believe everyone can hear me.
Yes, indeed, we can hear you. Thank you.
Okay, great. So yeah, and then we did interpret some results from the multiple logistic regression. If we have categorical variables, how do we interpret them? We saw that when the coefficients are negative, then it means that our odds ratios would be less than 1, and that would mean that the association, we have a lower the lower odds of the outcome in the category which we are reporting on, compared to the baseline or the one that is set as the reference level. And then we went further to say that, well, once we know how to interpret our models, but before we interpret them, we need to make sure that the models are actually good. At least we know how to do interpretation, but are the models that we are fitting, are they good enough? And so we looked at, we talked about two ways in which we can, make that determination. The first is testing the goodness of fits of the model to see whether some of the assumptions that are underlying the models are valid before we can go ahead to interpret them. So we looked at how to do some of the goodness of fit tests based on the multiple logistic regression models that we have fitted. And then how do we interpret them? So we looked at the residual analysis that we can do to assess the distribution of the the error terms. And then also we looked at the goodness of fit test, which is a formal test where we need a p-value. And what we said was that the p-value does not have to be significant, because if it is significant, then it means that our model is not a good fit. And then we looked at the Hosmo-Lemosho goodness of fit test as well, where you can test the overall effects of the model, or individual variable specific interpretations or diagnosis can also be done on those variables. So today we are building on that. So those methods that we describe are for the one model that we have identified as our best model. But now, how do we determine that one model? There is a possibility that we can fit several models, and then we can decide on which of them is best. So that procedure is what we am referring to as assessing the model fit. So how do we determine that if I have multiple models, which one of them fits best? And once I pick one of them that fits best, I can do I can look at the goodness of fit test to see how well that model is doing. So in linear regression, one of the most common metrics for assessing the fitness of our model is called the R square, or the coefficient of multiple determination. This R square, it means that if we have a value, which oftentimes we can convert into percentage, then it tells us the percentage or the proportion of the variability that is explained by the model. However, in GLMs, we do not have that kind of interpretation, or we do not have that kind of R squares that we compute. What we have is called a pseudo R square, which is trying to mimic the idea of the R square. So it gives us a metric. However, we have to be careful when interpreting that metric, because it does not represent the proportional reduction in the error by including all the independent variables that we have in the model. So it does not, when you see a pseudo R square, never interpret it as if it is the ordinary R square that we have in linear regression. Okay, so we are going to delve deeper into that. But before I proceed, is there any question that anyone has based on the previous class that you want to get clarification on? You just have 1 minute to type on the chat, or just unmute yourself and tell us. Question. Yes, waiting for any questions. Okay, so the assumption is that everybody is fine, everything is clear. If that is the case, then I'll proceed. So the pseudo R square that I have talked about, we have several types, and you would see why. I mean, it's not a good way of assessing model fits, but it can sometimes be very useful. The first one is called the likelihood R square, or some people call it the Cohen's R square. So this is a value that would be given to you when you fit the model. But the problem with this type of R square is that when the effects is higher, it does not reflect in the R square, which is something intuitively you would want to think about. That okay, so if my independent variables are explaining my response very well, then my R square should go high. But this is not the case for the likelihood ratio R square, which makes it not a very useful or a very powerful metric to assess the fitness of our model. The fact that even you can have it can show a very high odds ratio, but then the R square is not increasing, and vice versa. Maybe the odds ratio is very weak, but then we are not seeing a very small R square. So it's not that powerful. The other type of pseudo R square is called the Cox and Snell R square. The problem with this also is that, like the normal R square, the value always lie between 0 and 1. So when you reach 1, then it means that you have a perfect fit. And that in that case, in the linear regression, you will see that when you plot the graph, all the points will be lying on a straight line. For the Cox and Snell R square, that is the pseudo R square, what happens is that it does not reach 1. The maximum value that you can get from the R square is in the Cox and Snell R square is 0.75. And so when you want to convert it in terms of percentage, the maximum you can ever achieve is the 75%. And so that is also one of the limitations of using the Cox and Snell R square, even though most softwares gives you can report it as well. Then we have the Nagel-Kelkes pseudo R square, which tends to mitigate the disadvantage that we have seen from the Cox and Snell. And so that one, so because of that, it is very widely used. Mostly, that is what most people use all the time, because it lies between 0 and 1, so it can achieve that maximum value of 1. So you can, if you have 1, then you can say that maybe it's a perfect fit, or etc. And then we have an alternative method, which is similar to the likelihood ratio text, called the McFadden's R square. So again, that R square also had the same disadvantage as the likelihood ratio R square. And then a modification has been done, which is called the McFadden's R square adjusted. Obviously, like the name suggests, it penalizes for or adjusts the R square based on the number of explanatory variables that you include in the model. So there are several types of R squares that have been proposed. These are the most common ones, and the most widely used one is the Nagel-Kelkes R square. So like I have warned earlier, do not compare the values of this pseudo R square. You should not compare the Cox and Snell R square value with the Nagel-Kelkes R square, because we can already see that they are different. One of them is ending at 0.75, the other one is ending at 1. And so we cannot do a comparison that say that, okay, between these pseudo R squares, this one is showing a better performance or the other. But what you can do is that if I pick one of the R square values, like let's say I've decided to report on the Nagel-Kelkes pseudo R square, then if I have several models that are predicting the same outcome, so if my outcome is depression, for example, and then I'm doing a prediction, then I can look at the values of the two models, which one of them gives me the highest Nagel-Kelkes R square, and I will say that that one is having a better fit than the other model that has a lower value. But again, remember, you cannot interpret that R square as if it is the proportional reduction in the variability in the error term that is explained by the independent variables that you have added in your model. Is there any questions on this before I move on to some examples?
Sorry,
Yeah,
sir. Kindly, would you mind repeating, explain the Cox and Snell R squared? I didn't get it clear.
yeah. So the Cox and Snell, so like I mentioned, is just a metric. So the normal R square, what happens is that the normal R square that we have in the regression, the value always lie between 0 and 1. So if I have like 0.95, then it means that 95% of the variability in the error term is explained by the model. However, for the GLMs, or like the logistic regression, if we compute the Cox and Snell R square, the highest we can achieve is 0.75. So it does not go beyond the 0.75. So you cannot get a value that is, let's say, 0.95, because the formula that is used to compute the Cox and Snell R square is limited. It's constrained to not go beyond the 0.75 because of the way it is constructed. So that is what I was trying to explain. So there are formulas to do that, but I think I'm not presenting the formulas here because they are a bit complicated, and probably because of the audience we have here, not everybody would understand some of the concepts. So I'm just presenting at the higher level. The software will be able to give you those values. And so I'm trying to let you understand some of the, how do you even interpret those values that comes out of the software, especially if you use SPSS or any other statistical software. Anytime you fit the logistic regression, it would also automatically produce some R square values for you. So if you see the Cox and Snell R square, note that it would always be less than 0.75. And so its interpretation, you also have to be very careful about it. The Nagel-Kekels R-square can go beyond 0.75. Okay, so the Cox and Snell, if I have a perfect model, even if the model is so perfect, you will not see a value of 0.95 because the formula constraints is that you cannot get up to that level. And so that is why I'm saying that the widely used metric is the Nagel-Kekels R-square that most researchers often report that. Yeah, but there are also some other ones that, depending on your preference, you can also report as well. But if I'm doing a comparison, if I have two models that I have to compare them based on the Cox and Snell R square, I'll pick the model that gives me the highest Cox and Snell R square, even though that R square will be higher. Maybe it is 0.74 and the other one is maybe 0.34. In that case, I'll pick the one which is the highest. I hope that helps, Irene.
Yes, it does. Thank you.
Thank you. All right. So how do we fit this in R? So it's a very long explanation, but it's actually very easy to do using the software. So remember that we already fit our model, the multiple logistic regression model, which we called mod 2. So mod 2 was our model fit. So to do that, to get the pseudo R square, we can install a package called the DEX tools. And once this package is installed, we can load it in R. And then once it is loaded, there is a function in that called the pseudo R square. So when we say pseudo R square, we specify the name of the model. And then you can report all the different metrics that I have talked about. If you want all of them, then you can just specify all. If you just say all, then it gives you multiple R square values would be reported. So here I'm restricting it. I just wanted to give me the McFadden's R square, the McFadden adjusted, the Cox and Snell, and then the Nagel-Kekels R square. So because of that, I'll just put this vector C into brackets. Then I specify the different R square values that I want R to report for me. So here you see that the McFadden's R square is 0.06. Don't interpret it as it's a 6% reduction in the error variance by the model, because that is not how it's constructed. And then the adjusted, you see that once, because it's a multiple regression, multiple logistic regression model, if you add more parameters, then it has to penalize you, because when you add that, automatically your R square would increase. So the adjusted version of the McFadden reduces to 0.05. And then the Cox and Snell, it's giving us a value of 0.15. Nagel-Kekels is giving us a value of 0.07. So these results, you cannot compare them. They are not comparable. If I have another model and I want to do a comparison, then I can choose maybe in the Nagel-Kekels and then compare the value I have here, 0.75, 0.07, and I compare that with another the other model's value as well. Okay. So that is all that I want to talk about in terms of the R square value as one of the metrics for assessing how well your model is fitting to your data. The next concept that we want to look at, yes, Dennis.
Yeah, I have a question regarding to what you have just said, not interpreting it as a percentage. Then what the objectivity of that, like how do we then conclude at this range, like let's say if it's closer to 1, like the way we interpret the multiple and adjusted R squared, like the percentage of variation, if it's closer to 100, then possibly the model is performing well. So what is there any like criteria of determining the 4 tests you have shown? If it's closer to something, then you can now say that then your model is doing good. Thank you.
Yes, so if it is based on the Cox and Snell, for example, like I mentioned, it is capped at 0.75. So it means that a value that is closer to 0.75, it means that the association is probably stronger. The Nagel Kerker can go beyond 1. It can go closer to 1 as the cap. So if I have a value that is 0.9, that means that model is also doing very well. So you can use the maximum values that these models can attain and use that. What I'm cautioning against, you can also present it in terms of percentage, like 0.7. So you can just say that the 70% of the pseudo R square value was 75% or 70%. You can do that. But what you should not do is interpret it like a 70% reduction in the error variance, the variability in the error that is explained by the independent variable. So it is that interpretation that we lose by using this pseudo R square. So like the name suggests, pseudo means false, right? So it is a false R square. So it's not like the typical R square, but they are just trying to mimic how the R square is constructed from the linear regression model to come up with some quantities that we can use to do a comparison between models. Are we okay, Dennis?
Cool. Thank you. Thank you.
Okay. All right. So the next concept is also based on how. So at the models that we fit, if you want to see whether the model is doing well, then we want to see how well the model is predicting our observed data. So to do that, we would use these concepts. So I'm going to introduce this concept of diagnosis testing. So assuming that I know I have a medical equipment that medical equipment, it's helping me test whether somebody has depression or not. Okay. So maybe assuming that it is just some device that I put on you, and then if you have depression, it will be able to tell me that you have depression. And if you don't have depression, it's going to tell me that you don't have depression. So maybe it's a new method that I have designed, that I've proposed that, oh, this is my technique. It's very good. It can help me to detect whether somebody has depression or not. So if I want to test whether that equipment that I have is really good, can I sell this equipment? Should people use this equipment? Then I must, perform some diagnosis test on it to see how to convince people that, oh, this equipment is really good. So how will I do that? I can pick a sample of people that I know they have depression, and then also people that I know they do not have depression. So in that case, that is my truth. So we call that the truth. So I'm going to present that in this 2x2 table. So has the disease would mean the people that I know have depression. Do not have the disease are the people that I know do not have the condition. Then when I apply my new method that I said I can use to detect, I would count how many. So I would use my equipment to test these people, all of them, to see whether it is able to detect whether they actually have the condition or not. So there are so many things that can happen in that case. The equipment may be able to correctly tell me people who have had the condition. And so if I count those people, then I get this A. So that is the number of people that actually have the condition, and my equipment correctly identify them as having the equipment. There could also be people that do not have the condition, and my new device tells me that no, these people do not have the condition. So I can count the number of such cases, and that will give me D. All right. So those are the correct decisions that can be made by this equipment. But the equipment could also give us some errors. So probably it can tell me that somebody has the condition when in fact the person I know truly does not have depression, and yet the equipment is giving me a false result that that person has the condition. The same way, somebody may have the condition, but then the equipment or my new techniques is not able to detect that that person actually has the condition. So in that case, I have created again also two types of errors. And so based on this table, there are metrics that I can compute to actually test whether this equipment is doing well or not. So we have what the concept of true positives. So the true positives represent the people that has the actually has the condition, and my equipment is able to correctly identify them. We call them that the true positive. And the true negatives are the ones that the equipment correctly identify that they do not have the disease. And then the errors, the ones that give us the errors, we also have two types. So we have the false positive. So the false positives are the ones that were positive, were false or did not have the condition, but my test said they had the condition. And then the other one, they did have the conditions, but my test was negative. So we call them the false negative. Then the metrics that we can compute can be based on this false positive, false negative, true positive, and true negative. So we can generate a number of metrics based on that. Sensitivity is one of the metrics that we use, which tells us how good our equipment is in detecting whether somebody has the condition or not. So it is a ratio of the true positives divided by all the people that did not, the total number of people who I know did not have has the condition. So all the people that has the condition, how many of them was the equipment able to detect? We call that the sensitivity. And so you will see the sensitivity of my test or the sensitivity of my medical device. It means that, okay, so for all the people that have the condition, how many of them were detected to by the equipment to have the condition? Then we also have the specificity, which is the also the correct decisions based on the negative one. So all the people that have the all the people that did not have the condition, how many of them was the test able to correctly tell us that they did not actually have the condition? We call that the specificity. And so if I have a medical device that I want to test, or I have a test that I want to perform, then I'll always want to make sure that the sensitivity and specificity is very high. Unfortunately, you may have a device that is giving you high sensitivity, but then the specificity is very low. Or you could also have an equipment that has very low sensitivity, but then the specificity is very high, which is not something that you want. If an equipment or a diagnosis tool would be confirmed to be very effective, then it must give us very high sensitivity and very high specificity. If your sensitivity and specificity is very high, then it's very likely that the errors that are generated by that device would be very low. We also have what we call the positive predictive values and then the negative predictive values. The positive predictive value is also a ratio where the denominator is all the positive tests that the equipment has given us, and then we want to know which one of them are actually correct. Which one of all the positives that the equipment has detected, which one of them were actually correct? So you can just take the true positive divided by the true positive plus the false positive. And then the negative predictive value is also obtained in a similar way. Apart from that, there are several other metrics that we can compute. One of them is, for example, the accuracy. So the accuracy is the correct decisions, the true positives plus the true negatives, which we know are the correct decisions, divided by all the other cells, the total sum of all the cells that we have here. And so if I know the accuracy, then I'll be able to tell what the error is. So the error, I can actually compute the error by taking the false positive plus the false negative, and also divide by the total number, the true positive, false negative, false negative, and then true negative. However, because I've already computed my accuracy, I can just take 1 minus the accuracy, and that will give me my error rate. We have talked about the positive predictive value, negative predictive values. Those are metrics that we can generate from that. Sometimes the positive predictive value is also called precision. And then in other places, you would find that the sensitivity is actually also called recall. So they have precision, which is the positive predictive value, or recall, which is also the same as sensitivity. And then we have the specificity. And now also we have the detection rate. So detection rate is also just picking how the equipment is able to detect positive results. Okay, so the true positive divided by everything else. Okay, and that is the detection rate. And then we have the balance accuracy, which is an average of the sensitivity and the specificity. Remember that we said that we want both of them to be very high. So it means that the balance accuracy would be, kind of an average of the metrics that we can also use to compare whether a device is doing well or not. And then we also have the prevalence. Prevalence is just of the conditions that the condition that you have. That is the disease that you have. So we have the in the true positives, and then the false, the true positives and the false negative column. We said that if you add the two, it's just telling us all the total number of people who have the condition. So if I know all the people that actually have the condition, and I divide by everything else, then that gives me my prevalence. Okay, and then we also have the detective prevalence, where then we focus on the true positives and then the false positives as another metric. So there are several metrics that are available that we can also use to. So we are going to learn from this to say that, okay, so now if I have a logistic regression model, how can I use this concept of the confusion metrics, or these metrics that we have talked about? How can I use that to actually test whether my model is performing well or not? So what we do is that we have collected data. So we have the observed data, like the depression data that we have. We already know the depression data, those that are have depression and those that do not have the depression. And that is what we use to fit the model. And then we added the independent variables so that we are able to see whether there is an association with the response variable. Now, once we fit the model, we can actually ask that, the model is not always 100% accurate, but the model is just trying to describe what we have observed. Okay, so once we fit the model would be able to correctly predict some of them, but some of them it may not get right. So it means that if we have the predicted values, what the model is predicting for me, and what I've actually observed, then I can also create this 2x2 table where I have the observed as the truth, and then what the model has predicted as the test score, which I have here. So maybe here I would have depression and then no depression here by the model. And then here I have depression and no depression according to the data. And then once I have this, I can count the numbers, and then I'll be able to compute these metrics that I have generated here. I can compute the accuracy. So the accuracy will now be on the model. So how well is the model predicting the true positives and the true negatives combined? And then I can also compute all the other metrics. So if I have several models that I fit, then I can compare the accuracies of these models and then make a comparison with that. Okay, so let's pick an example, a classroom example. So assuming that a hygienist at the university dental clinic screened 220 patients for an acute periodontal disease. Okay. Later, a careful examination was given, and the results indicated that 45 were true positives, 40 false negative, 26 false positive, and 135 true negatives. So based on this information, we can fill the table. We know that the first column is the true positive, so that is 45. The diagonal one is also the true negative, so we have the true negative here, and then we have the false positive, which is the 26, which we have here, and then we have the false negative, which is the 14, which is here. So we have just used the information that has been given to us. When we add everything, we get 20. So if we want to know what the sensitivity of the this examination is, the examination that was done by the periodontist, if you want to know the sensitivity, then it means that, remember, we need to, this is the test part and this is the truth. So the truth is what we have on this side, and then the test is what we have from here. So what will be our sensitivity? We add these two values, which gives us 59, and then we divide that by 220, and that will give us the value for our sensitivity. And we can use the same idea to compute the accuracy. So if you want the accuracy, we add all the diagonal entries, which is the 45 plus 135, and then we divide that by 220, and that would be the accuracy of our model. So it means that in this particular case, the examination that was done by the periodontist, it's giving us an accuracy of 82%. So we can try on your own all the metrics that we have described based on this example. How would you compute all of this based on the, so for example, what is the prevalence? How do you compute the prevalence? How do you compute recall? How do you compute specificity, etc., etc.? You can get all of that just by constructing this simple table. So try it at your free time so that you can practice and understand the important how these metrics are computed. The software will give you, but it is up to you to now have the understanding of what is being generated by the software. Because if the software produces something that you do not understand, then you cannot interpret them correctly. So I'm bringing these things up now so that at least you understand when you see these values in the future, you know what they mean. Okay, now I want to use the same example that we have done. I want to use R to be able to do it. Here I'm going to use a package in R called the correct package. The correct package is one of the packages that are used widely for machine learning models. So those who are interested in machine learning in R, this is one of the powerful packages that is available in R for doing machine learning algorithms. So it fits several machine learning models. And so there is a function in there that can help us to compute these metrics so that the machine learning algorithms that we build will be able to do a comparisons based on that. So here I want to create a matrix. So in R, to create a matrix, we put all the data in the vector form, and then we specify 2 by 2. So because it's a 2 by 2 matrix, we just specify 2 by 2 matrix. So matrix into brackets, and then we specify all the values that we have. So we go from column to column. So this is how we go in the table that we know we have a 2 by 2. We just start listing the values like this, and then we go like that. And that is how we have it here. And then you can have the 2 by 2 ask R to now convert that vector into a 2 by 2 matrix. Once you have this 2 by 2 matrix, we can just say, put the function confusion matrix, and then the name of the matrix that we have created. Once we do that, and we run the model, it will give us all the metrics that we are struggling to compute by our hand. It's given to us free of charge. Okay, so you can see that the accuracy that we did was 0.882, And then you see that the software is also correctly giving us 0.8182. So if you approximate this, then you get exactly 0.82. All the other metrics that we talked about are here. You have your sensitivity, you have your specificity, you can confirm and see what you actually get. We have the positive predictive values, negative predictive values. We have the prevalence, we have the detection rates, we have the balance accuracy. We have everything that we have talked about by just running just one command, confusion metrics, and then we put the actual metrics that we want to compute the metrics on in it. Okay. Any questions so far before I proceed? Any questions from anyone? Any pressing questions? Yeah, really, Johnson. Please go ahead.
Yeah, thanks so much for this informative discussions. I would just like to try to see if we can have a live example using our previous data set.
Yeah.
To see now how we can use the confusion matrix to come up.
Yes, we are going to do that. So that is coming next.
Okay, thank you.
All right. Okay. So this is just to describe the concept so that you understand it, rather than me throwing everything at you and then you are now trying to figure out, okay, so what is this? What is that? But now everything is very clear. We see that it is just a 2x2 table, and then we are just trying to pick these values and then trying to understand them. Okay. All right. So the next, so now we want to, so this is an alternative way. If I want the table to look like my, the one that I display where I have the predicted positive, negative. So this is just an example. It's just the same thing that I have done, but in a better way for people who wants to present their results in a very nice way, as based on the example. So it's exactly the same. I'm not going to spend time on this. Just go through the slides, and then if you have any questions, you can ask. Yes, so now the question that our brother asked us, how do we test this? How do we use these metrics? How do we perform it? How do we perform the diagnosis? So this would be better. So I'm just going to switch to the R code so that we do everything from there. We see what the results are showing, and then I come back to the slides. So let me stop sharing the slides, and then I will show my R's. Okay, so I believe you can see my slides. So I have to run all the things that we ran before so that I have the models. So I'm going to run through everything. So the last model, model 2 that we did. So this is the model 2. So the model 2 is our model that we want to see. How do we compute these metrics to assess whether our model 2 is actually performing very well or not? So our model is depression, which is yes and no, which we have coded as 1 and 0. And then we have the independent variables, sex, age group, blah, 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 blah. And then we specify the name of the data, and then we specify the family. We now understand why we need to specify the family, because the GLM, there are several members of the GLM family. So we need to specify which particular one are we using. And then we have to indicate that we want to use the length function that transform the outcomes to -infinity to infinity, because the binary data is just 0 and 1. So we fit the model, and the model is called mod 2. We want to interpret it, we just run and we use the odds ratio. But now we want to assume that the model has now been fitted, and then now we want to see how well the model is predicted. Okay. So the R square that I talked about. So let me run this so that we see all the results again in R. Let me hide this here. And then you can always do question mark pseudo R square. And you can always get the help. Okay, you can always get the help here. So I did mention that you can also, if you want to get all the R squares that the package has, you can just instead of specifying all the name of the R squares that we want to report, we can actually say which is equals to, then we put all. We'll just say all of them, so that it gives us all the different R squares, the pseudo R squares that are available. So you can see that there are other ones that we did not talk about. We have the Efron, we have the Adrich Nelson, we have the G2, the likelihood ratio. We talked about the likelihood, the likelihood and the log likelihood R square. Okay, here it's producing some other metrics which we will look at later on. We also have the Mark-Levis, Zaviona. You see, there are several pseudo R square values, and so you can get all of them in R if you so wish. Okay, now let me go back to my my example. Okay, so now this is we have fitted our model. It's called mod 2. Okay, so in our data sets, if I view my data, so let me click on my data. I'll see that in my data, I have the 0 and the 1s, right? I have 0, 1, 0, 1, 0, 1, 0, 1 as my response variable. Or if I want to use the depression, I have no, yes, no, yes, no, yes. So I have some no's, and then I have some yes values which are here. And then the y's are also on this side. Okay, so this would serve as my truth. So this is the truth that I have. Then I now would want to now see how well my model is predicting. Okay, so I'm going to run this line. I'll say predict. I'm going to use my model. So I specify mod is equals to our mod 2, just specify the mod. The name of my data that the model should use to do the prediction. And then I'll specify type here to be the response that it should predict the response variables. I want to see the predicted responses, and not the if I use the other option, then the software will just give me 0 and 1, 0 and 1, but I want to see the predicted probabilities. So when I run this line, I am saving the results again. So that $ prep P means that I want to save the predictions that the model will give me. I want to add it to this. Okay, so I'm going to run this and then open the data again to see what has been created. So when I open the data, you see that I have this column which is depression. I have my responses which are 0 and 1s, but then I have the probability. So because I asked it to give me the probabilities. Okay, so the probabilities is this column. Now, the probabilities that it has given me is not the same as the response. So remember, our response is 0 and 1. And from the logistic regression, we said that we use the probability, we take the log transform of the odds. And the odds is the probability of getting depression divided by the probability of not getting depression. So that probability of getting depression is what has been given to us here. So based on this probability, we can now use the probability to now say, okay, so how is the model predicting my outcome Y? Okay, we want the Y, the y predict should be 0 and 1. We want to see whether the model is deciding very well. Now, for us to do that, we need to determine a cutoff point. We have to assume a cutoff point because the probabilities are between 0 and 1. So if I run all the that $, the predicted probabilities, we see that there are just so many values between 0 and 1. There are so many. Some of them are not achieving 1, some of them are 0 point something. So there are so many probabilities that the model has been able to predict for me. So I have to make a decision to say that, okay, if the value is 0.5, if the predicted probability of my model is 0.05, then the person has depression because that probability is high. So if the probability of getting depression is high, then I will say that, okay, then that person has depression. But if the probability is low, then it means that the person do not have the probability. So I need to determine a cutoff point. So we'll come back to how do I determine what is the cutoff point. But in this example, I am deciding that the cutoff point I want to use is just 0.04. Okay? My cutoff point that I have chosen is 0.04. So I want to tell R that if the predicted probabilities that I have obtained, if they are bigger than 0.01, then it means the person should be said to have depression. Otherwise, then the person should not have depression. Okay? And so when I run this, so I'm going to run this line again, and then I can open my data set, and then I'll see that that has been created. So before we had just these probabilities, but now we also have the predicted y's. So here, what I observed was 0 or no depression. If I compare that with this, then this one has no depression, and I also predicted that it is no. Here again, no, I also predicted it is no. No, 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 no. But there could be some places where maybe the model is making an error. So like here, this particular one is a yes, and my model also said what? No. Okay, so you see that here the observed depression was actually yes, but my model says no. Okay, and so I can see that some errors have already been made, but some are also very correct, and so I can use this information to tell me whether my model is doing well or not. So that means that I can use this to count the number of yes, yes, no, yes, yes, no, and then yes, yes, so that I get that 2 by 2 table that I can now use to do the confusion matrix. Okay, so I'm going to do that. Some data management. R requires that the new variable that I have created, it wants it to be a factor. So I convert it into a factor. It doesn't change anything. It's just a data object will now be a factor. If I open the data, it's still going to be the yes and the no, yes and the no. So nothing has happened to that. And then also the depression variable also has to be a factor before I can compute. I can use the confusion matrix. So again, I've also converted that one into a factor by saying that as.factor is equals to that. Now in R, when we convert the variable, we tell R that this variable is a factor, then it's able to create the dummy variables. But if your data is in character, or if it sees it as character, some of the packages, they will automatically convert the character into factors for you. It will automatically do it for you. But there are certain packages that you have to tell it that this particular one is a factor or is a dummy. You want the software to convert it into a dummy variable before that will be done. So in that case, it is always important, or it's very good that if you have a categorical variable in your data set and you want to fit a model, just make sure that they are all converted into a factor by saying as.factor, and then you specify that particular column. Now, once that is done, we can use that package that we talked about, which is in the current package. Let me run the library caret to be sure that I have run it. Okay. So that is the caret package that I have loaded. Now I have to specify the 2 columns. So here I'm not specifying a matrix. You can specify a matrix, which is what we did in the example that we did before. But here you can actually specify what is the true one and what is the predicted, because we don't want to do the counting ourselves. We are lazy. We don't want to do the counting ourselves. So we want the software to do the counting for us. And then the positive, which one are we modeled? The ones that we have modeled is the model, we have modeled the yes. The yes is the depression, probability of depression. So we want to tell the package that we are interested in the yeses and not the no's. We are not predicting the probability of having no depression, okay? But we are predicting the probability of having depression. So the positive here is yes. So I'm going to run that line. So I have have no errors. So now when I run this matrix that I see matrix, which is the confusion matrix, then I'll see that it gives me all the metrics. So it has created the table for me. Okay. So here is the table. The reference. So here it gives me a reference, which is what we used to call the truth, and then the prediction, which is what the model actually predicted. And then you see it has the yes, and then 82 of the yeses were actually correct. Okay. And then the no's, 8243 of them was correct. So you can see that in terms of sensitivity, the sensitivity will be very, very low, because it's just a few of them. The depression cases were actually detected by the model as being having depression. Okay, so we have only 82%. So having this 82% means that our sensitivity is going to be very low. But if you look at the no's, for majority of the no's, the model predicted correctly that they actually do not have the depression. So in that case, our specificity is going to go high, right? Because then it has captured most of them. And now here it's because our model, the prevalence of the condition was very, very small. Okay, so I'll come back to that later on. But in terms of accuracy, the model is saying that I have an accuracy of 0.8865, which is very strange, right? But we know why it is so. So that is why when you look at accuracy alone to tell whether your model is doing very well or not, that can be very misleading, because you can already see that our sensitivity here is very, very low, which we can check from the results from here. So look at this sensitivity. Sensitivity was only 8%, but specificity was very high, almost 98%. Okay, and so if I am comparing different models and I'm just relying on just the accuracy may be very misleading. And that is why it's important you also look at the other metrics. So you can look at the sensitivity, you can look at the specificity, and you can say, yes, based on sensitivity is very high, but specificity is not good. If you can look at the balanced accuracy, you see the one that combines sensitivity and specificity is 0.53 compared to the accuracy, which is giving me a value of 0.88. Okay, so you can use this type of information to tell whether my model is actually doing very well or it is not doing very well. And then you can also compute the error rates. So the error rates based on the model will just be 1 minus this value here, and that is will just be what the error rates by the model. But it's important you also look at all of the other metrics, even when you are making a decision on which model performs better or which models performs worse. Okay, so here, this is based on me choosing a particular value, 0.04, as my cutoff point. How did I come to that? For me, I just, I mean, this is a value that is very subjective. Somebody may say that, no, that probability is very small, or maybe that probability is very low. Why did you pick that value, etc., etc.? Okay. So For me, I just use a guess because I know that the prevalence of our of depression in our data was about, I think, was it closer to 4%? So we can do that now. Let's say, let me say table data depression. Okay, there are about 2, 4, 8 cases that have depression. If I divide that by 1943, I have almost like 0.03, 0.03, 3%. So I have only 3% of depression. And so it means that my data is not that rich enough that I can get higher probabilities of getting depression. Because the data, the one that I'm using to build the model, does not have a lot of cases. So my cutoff point, I can gauge a cutoff point that is around that particular figure. That would help me to be able to classify this. Most softwares would use a cutoff point of 0.05, which we can use, because if I tell R that it should give me, it's like when I use this predict function, if I ask it to just give me the predictions directly by itself, then it was going to use a default value of 0.05 as the cutoff point. Okay, sorry, 50% as the cutoff point. So it's going to give me use 0.5 as the cutoff point. So it would have put 0.5 here as the cutoff point. So when I do that, so I can actually do that, right? So I run that model, okay, save my data again, run my depression, save my confusion matrix. Then you will see that there is actually no data. I'll get an error term, an error figure, okay? That the data cannot have more levels than the references. Let me see whether it is the error that I was expecting. Let me open the data again and go to my data. Yes, so it actually has the yeses and the nos. But when I do table that, and then I do the predict this new one, you see that it's only gave me nos. It only gives me no's, but it is not able to give me a yes because the probabilities that I have are so small that they are not going to give me any yeses. Okay, so determining what is the best cutoff point to determine your prediction is very, very important. If your prevalence is very high, then you can use higher probabilities. But if you have very small or situations where the outcome is very rare, then it is better you use a cutoff value that is actually very small. Okay, somebody can say that, okay, then since you use a value 0.4, why not use 0.2? So what will 0.2 has given us? So I can run the model again based on 0.2 as the cutoff point, and then I'll run my model, okay, and then I'll get accuracy. Now when I use the 0.2, my accuracy has actually dropped. I now have 4198%, but it looks like I have a very high negative positive predictive value. Okay, I've had a very high positive predictive value, very low negative predictive value. My specificity is still very high, but my sensitivity is still very bad. Okay, so I have to look at all of these metrics even as I make a determination on which of the which model do I need to use. Okay. Somebody is asking the McNamara test. McNamara test. Yes, so I have not commented on this. The McNamara test is just telling us whether there is any association between what the observed value is and what the predicted value is. Okay, so it's just measuring. So here it's giving you a p-value which says that it's significant. So if it is significant, then it's just saying that whatever I am predicting, and then whatever I am observing, it's not statistically significant. So the observed and the predicted, in terms of comparison, there is a significant difference between them. In this example scene, what conclusion will you draw in the performance of the model? Yes, I cannot draw any conclusion yet because there are still other things that we need to do. So I'm bringing all of these issues up so that we can begin to, even if when we fit our model for our depression data, we should start thinking about, okay, how do I even assess my model in a more efficient way? How would I really tell whether my model is doing well or not? If you just report the accuracy, and I have a very, very big accuracy, and then you are so excited, but then you would realize that that accuracy is actually because maybe sensitivity is very, very high, but probably that model is very bad in terms of your specificity. Okay, so can you use the prevalence of depression from as a cutoff point instead of the guess? Yes, that could be an option, but it is still something that you can explore. You can still think in terms of, okay, if I have another cutoff point, use that cutoff point to decide whether which one would be a better option. Okay. So the cutoff points, let's leave it at this level. So you will see that there is another part of the slides that we come to that can help us to determine what the optimal cutoff point is. All right. So we can have an optimal cutoff point based on the data that we have. But even that is not always very good because there are several ways of determining what the optimal cutoff point is. Okay. So we'll come to that and I can explain more into details how we can assess our model performance. Okay. All right, good. So I guess that is it. So let me switch again to my slides. Unless there are questions on how we can use the model to assess our model performance. So let me share my slides again. Okay, great. So the results we had is what we have on here, produced on the slides. All right. Now we want to look at another metric for determining whether my model is doing very well or not. That method is called the receiver operating curve, or called the ROC curve. So one way of determining whether our model is good or not. So when can you say the model is good? When can you say the model is good? Maybe at the end of this class, this section of logistic regression, that will be the question that I'll be asking you at TEM. So gather all this information that I am providing you, and then at the end of the lecture, you should be able to help me to answer the question, can I say that model is good or not? Okay, so I'll throw back that question to you. And that is why modeling is it's more like it's a skill. Like there is no straightforward answer. You know, there are so many things that you have to look at. You know, and it's not just oh, I just plug in my data into the software to do the thing for me, and then I quickly go to accuracy. Most people like the accuracy very much, or recall value, and then you just you know, say that, oh, I have an accuracy of this, and so my model is doing very well. And this problem is not just about statistical modeling. Currently, we are seeing the same type of you know, misconception or errors being used, in, especially when people are assessing the performance of machine learning algorithms, not just for logistic regression, but sometimes people are doing random forest, they are doing, you know, tree-based models, and then they are also making these predictions, and they use some of these metrics, and sometimes the interpretations are sometimes a bit problematic. So when, as a reviewer, when you review an article, you also want to interrogate not just the accuracy, but you also want to see other metrics, how well those metrics are doing, because we know that the accuracy can be very misleading if it is being dominated by just one aspect of your model performance. Okay. So the next approach is the ROC curve. So ROC curve is also one method that we can also use to assess whether our model is fitting very well or not. And what is this ROC curve? We know how to calculate the sensitivity. We know how to compute the specificity. So it is just a plot of sensitivity versus 1 minus specificity. Okay. So how do we draw a curve when we just calculated one value for sensitivity and one value for specificity? Now, what the ROC curve is proposing is that I can give a range. Remember the cutoff points that I gave. I chose 0.4, right? But I know that 0.04, I know that the cutoff points can lie between 0 and 1. So I can pick a cutoff point of 0, calculate the sensitivities and specificity, pick a cutoff point of 0.1, calculate sensitivity, specificity, 0.2, 0.21, 0.3, 0.4, 0.004. I can pick a range of several cutoff points that is ranging from 0 until 1. And each of them, I'm going to compute my sensitivity and I'm going to compute my specificity. So it means that I would have a lot of values for sensitivity and specificity according to the threshold values that I have provided. So the threshold values, I'll use all of them, order my outcomes. Then I can plot a curve. Okay. So that curve that I plot is what we call the ROC curve, receiver operating characteristics curve. And so when I do that curve, I can calculate the area. I can draw a straight line, okay, on the curve that goes through the 45-degree angle. And then I calculate the area under the ROC curve. It's one of the metrics that we can use to determine whether our model is doing well or not. Okay, so we can construct an ROC curve, and then the area under that ROC curve would be the metric that we can use to say that my model is performing well. Because remember, the model's performance, as we have seen, can be based on the cutoff points that we have used. Okay, so if we want to assess how well the model is doing, then it will be good to know how well the model will do for all possible values of the cutoff points. Then after, I can then summarize the information and say that, okay, this model is really doing well, because then it does well even across all the different cutoff points. And so that is why the ROC, the area under the curve, which is the AOU, is another metric that we can use to check whether my model is doing well or not. I can construct the ROC curve for the data that we have done in R in a very simple way. Okay, so let me switch back to R, and then we go and see if we can calculate our ROC curve. I think I should share my entire screen. Share screen. Let me share this screen. Okay, then I can switch between. Okay. All right. So we want to see how do we plot the ROC curve. So at least now you understand the concept behind ROC curve. So it's not very complicated. We are not going to do it by our hand, but let's have an understanding of what the ROC curve is actually doing, because we know that it's just the cutoff points, and we know the value, what the use of these cutoff points are. They tell us we can use the cutoff points, get the predictions, and compute the sensitivity and specificity. And so the cutoff points, we can have several possibilities. We want to pick a big range of cutoff points, use that to compute sensitivity and specificity, and then we do a plot. We plot that. And then based on that plot, we want to assess whether my model is good or not. Okay, so there is a package in R called the ROCR, okay, which we can use So I have to load that library. So first of all, you have to install the package, use install.packages, and then the name of the package in parentheses, no, in inverted commas or quotations. Then we load it through the library command. Okay, so I have loaded my ROCR library. Then the first thing I need to do is what? I need to get the predicted probabilities, as we said. So I'm going to run this line. Okay, so here I have saved it as P. I can save it in the data. I didn't want to save it in the data, so I've just given it a value called P. Okay, and so this P, if I run this P, it's just going to be the like before, just the predicted probabilities. Okay, then I want to create a prediction matrix. Okay, so there is a function called predict, where it now compares the predicted probability that I have with the values that I have in my data. Okay, so I can run this, and when I run this, this is an object that is created. When I run it, it just gives me some it doesn't give me anything. Okay, it just tells me that I have 9391 data points. Okay, now this object, I'll now use it to compute use a package in this a function called performance, which require me to enter this new variable that I have created based on this prediction value. I put it here. Then I specify the ROC curve that I want. Based on what metric do I want to construct my ROC curve? So here, if I want to know much more, remember that I told you you can have several different metrics based on the metrics that we have talked about. So it can be the positive predictive values. It can be based on so many different metrics. If you want to see what this function can offer, you can just do question mark and then you type performance, and it will tell you all the different possible measures that you can use when you want to conduct. So you can use the error rate, you can use the false positive rate, you can use the true positive rates, etc., etc. So you can have several options that you can use if you want to get the ROC curve based on a particular metric. So here the ROC curve is based on the true positive rates and then the false positive rates. And so I would use the function performance. And then once I run this, it creates this object for me. Okay, so this object would be so it will give me all the cutoff points. So all the cutoff point is called the alpha value. It will just pick a range of values by itself. So it gets a whole range of positive values for me. And then once I pick this object now, I'll just run this model, run this plots command, which now gives me the curve. So I see that it plots. Also, I have the false positive rate and then the true positive rate. So my ROC curve is based on this. Remember, I said the false positive rate was the same as the sensitivity was the same as sensitivity. Sensitivity was the same as recall. So sensitivity is the true negative. Okay, so this ROC curve is based on the true positive rates and then the true negative rates. But you can decide on which metric you want to your plot to be based on. So here it is based on the false positive rates and the true positive rates. And then I can draw a line. So the area under this curve is what we call the AUC. Okay, so if a model is doing very well, then I expect that this curve would be very closer to the top corner here. All right, so that means that if my model is if the false positive, so it would have been best to do the sensitivity and specificity so that you understand that the more if this model is doing very well, then I'll expect that the curve here will be moving closer to the corner here. Okay, that is so. If the model is very perfect, then I should see a curve like this. So if I see a curve like this, then it means that the area under this curve will be very big. Okay, but if I have a curve like this, then the area under this curve will just be this small area. That will mean that my model is not doing very well. Okay, so a model that is doing very well should give you an ROC curve that looks like this. All right, in that case, then I'll say that my model is very good. But then I can also compute the area under the curve. So if I have two models that I want to compare whether the performance of those two models, then I'll just compare their ROC curves. All right, and I can draw a straight line under it. Now, how do I get the area under the curve? I can use the predict values that I can now predict the AUC based on that. Remember the same function that we use here. Here I use it to predict the true positive rate and the false negative rate. I can also use the same function to predict the AUC, that is the area under the curve. So when I do that, it gives me a value, and I want to plot that value on my graph. So when I plot the value on my graph, I get the area under the curve is 0.7. All right, so the area under the curve for this particular model is 0.7. Okay, so here you cannot say the 0.7 is high or it is low. You can only say it's high or low depending on another model. So I can pick another model, also compute its area under the curve, and then the one that is higher, I would consider that one model as performing better than the other. Okay, so that is how ROC curves are constructed, and how we can use the area under them to be able to determine whether our model is doing well or not. Now, another good thing about the ROC curve is that it can help us to determine the cutoff points. So remember, we said that the cutoff point is very subjective. You can use, you can use your own cutoff points, but then somebody else may use another cutoff point, and that person's cutoff point will be giving better prediction of the model than yours. Okay, so what we can do is that if we said that the model, cutoff, so if the curve is like this, okay, that means that if I have sensitivity here and I have 1 minus specificity here, okay, 1 minus specificity means that if my sensitivity is higher, I also want my sensitivity. If my sensitivity is high, I also prefer a model that gives me higher specificity. Okay, so 1 minus specificity would mean that I need a lower value for that particular. So it means that when I have higher value of sensitivity, then I want to get what? A higher value also for the specificity. So it means that I can, if I have a curve like this, then I want to get of all the cutoff points that were used to plot this curve, which of the cutoff points gave me the highest sensitivity and then the highest specificity. Then I'll pick that particular value and use it as my cutoff points. Okay, so that is how the ROC curve can also be used to help you detect which is your optimal cutoff point. So it has a lot of advantages. Can help you to detect how well your model is doing based on assessing the area under the curve. But we can also use it to test whether to determine the optimal cutoff point. Chris, you have a question that can you also use the PROC curve? And the answer is yes. So I have also done that below here. So you see there's another library that you can use. Like I mentioned, R is full of several packages. You just have to understand the concept that you are using and you can get an appropriate package in R that does it in a way that you like. Okay, so yes, Hunde, you have your hand raised. Please go ahead.
All right, thank you, Doc. Just I want to really differentiate whether this rock is only used to check the model performance for logistic regression or for like linear regression as well.
Yes, it can also be used for other type of models. So you can use it for you can also use it for this predictive model. So random forest, you can use random forest to also predict yes or no. You can use decision trees to predict yes or no values. So as long as the model is giving you any model that is predicting a yes or a no value, you can still apply the ROC curve because it is going to give you a predicted probabilities, and then you can do you can compute these metrics as well. So it depends on the type of model that you are using, but it's not for linear regression model. It's just for binary outcomes.
So it is only used for binary outcomes.
Which one? So the sensitivity and
Rock.
specificity is based on the binary outcome. Yes.
All right. Okay. Thank you very much. Yes. Please, can you share us the data because that the shared data is not open, please.
The shared data.
Actually,
Come
one
again.
data is shared. The data is shared on the WhatsApp, but that data is not open.
Okay, so I think
I mean, just I want to really practice on that in order to well
okay.
understand the practice.
Okay, and then it means that Joel, you need to respond to that. The CSV, I sent a CSV file, and so you can use the CSV file, share the CSV file with them, and then you can reload the data straight away. Yes, Andrew, you have a question. Go ahead.
I actually wanted to tell him that it's in the package shared.
It's in the package shared, right? Okay, so yeah.
Yes, I'll put it in the chat. Kindly check.
Okay. Yeah, I'm not on the platform where they are sharing the information, so I may not know. Yeah, okay, so the link is also provided on the Google Drive where all the information is placed. So you can click on that, and then you should have access to the zip file. So the file is zipped, so you have to unzip the file. If you don't unzip the file, then you cannot open it. So you have to first of all unzip the file, and then go and get the content of that file. That is where the data will be found. Okay. All right. So, like I mentioned, there are also other packages like the PROC curve, PROC library, which we can use. And here, I am using it to determine the optimal cutoff points. So this package did not, I did not find a way of getting the optimal cutoff points from this, from the model using this package. So I reverted to this library, which can also give you a plot of the ROC curve and all the things that we have done. But additionally, it can also give you the optimal cutoff points that you can use for your model. So you load the library. So once you load the library, then you don't need this part of the code. But sometimes there are other packages that also has a function called ROC. So if another package has a function called ROC, and then you want to use the ROC function, which is in this package, you may run into an error because the R will be confused and will not know which package you are using. So here you can specify, if I want to say that I want the ROC function that is coming from this particular package, then you put the name of the package and you put two columns. You put two columns, and then you can now apply the function. So that is what I have done here. So when I run this, so I specify the data, my actual cases, and then I specify the probabilities that we computed, and then I use the coordinates. I use this function called cots, to pick the actual best cutoff points. So you specify these things that ROC curve that I have computed from here, and then I'll say I want the best. Then the method is that I want the one. So it depends on which metric you are using, what have you plotted. So you could have a curve where you are interested in higher sensitivity and higher specificity. In that case, you want the corner here. But maybe you want a low values here, high values here. Then it means that when you do a plot, then your plot will be like this. So in that case, you want to report what is at the corner here. Okay, so here we want the closest to the top left value to be able to be the one that is picked as the best or optimal cutoff point. So I'm going to run that, and then I print this. So when I print this, the package is telling me that the optimal cutoff point is actually 0.026. So this optimal cutoff point is going to give me this highest level of specificity, and then this level of sensitivity. Okay, so here it means that it's not giving me very high sensitivity and low specificity, but then if it's saying that if I use this particular cutoff point, then I'll be getting what a specificity and sensitivity around this particular value. Okay, I try to see whether if I use this optimal cutoff point, which is 0 points, so I can put it here. Let me say it is 0.26. So let me use 0.026 as now my cutoff point. So now I'm going back to my my model. I'm going back to how we were doing the predictions to compute the metrics. So first of all, you have to predict, then you have to use that cutoff point to get the responses. You convert them into a factor, the same for the depression value, and then you can plot the new one that you have created. Okay, so when I do that, based on what the software has given me as the optimal cutoff point, I get an accuracy value of 0.56. However, the promised cutoff points for sensitivity and specificity was not that close. So we need to find out why it is the case, because the software is telling us that the optimal cutoff point is 0.026, and it's supposed to give us a sensitivity of this and specificity of that. Okay, so maybe it depends on how the data is arranged, but yes, this is just a way of getting the optimal cutoff points and using the optimal cutoff points to be able to determine which model is what is the optimal cutoff point to use. Could you please share the link with materials for all series? Some of us were not able to join all the sections due to conflicting schedules. Thank you. Okay, if Bernard is referring to this, I think that I believe they are recording these sections, and probably they will share the link with you later on. Okay. All right. So you can just go through again, just go through the slides and some of the things, run the models and test them yourself, and then you'll be able to get some of this. Then probably the last metric that we'll talk about that one needs to look at when determining the fit of the model is using this particular metric. So we have the log likelihood. So we can, if I have two models, logistic models, and I want to detect which one is higher, I can compare their log likelihoods, or another metric called the Alkar-Case information criteria. So the Alkar-Case information criteria is defined by this, which takes the -2 of the log likelihood and then penalizes it for the number of parameters that you have in the model. Okay, so if a model is doing well, then its likelihood has to be very high. So the likelihood of that model should be very high. So if you take the -2 of the log likelihood, then it means that we want the AIC value to be very small. So if I look at two models, then I'll pick, and I want to decide based on the likelihoods, then I'll pick a model that has the higher likelihood. But the problem is that if I add more parameters, then that's the model that has more parameters is going to give me a higher likelihood value. In that case, the -2 log likelihood will be very small. And so we need to penalize this model. So we add 2 times P to this as a penalty term. All right. Another metric which is also very commonly used is called the BIC. So AIC and BIC. The BIC is also based on the same principle, but then it penalizes not only on the parameters that you have in the model, but also your sample size. So assuming that I'm fitting the model where some of the models, when I fit them, some of the sample sizes will decrease. Maybe some models, if you have missing data in one of the independent variables, it will delete that data completely. So in that case, the sample size is going to reduce. So if I am doing a comparison, then I want to be able to also penalize based on the sample size. So it means that for some models, I may be able to get higher sample size when after I have fitted the model, but for some, I may get less. So you can also penalize based on the sample size that you have. But AIC, as long as your sample sizes are the same, then you don't have any issues. Even you can still use the BIC, or you can still use the AIC as your metric. Now, for all these metrics, if I want to use the -2 log likelihood, which I can use on alone, then a model that fits well gives me the lowest values. So any value that is if I have models, any value that gives any AIC value model that gives me the lowest AIC value or the lowest BIC value, I'll consider that model as best. Now, how is that so? Because the idea of AIC and BIC values is that it is measuring how well your model is fitting to your data. So it looks at it's like picking the difference between your model's performance and then what you have in your data. So if I take the difference between them, then I want a model that is doing well should give me very small values of whatever my model is predicting and whatever I have in my data. And that is why we need smaller values of that model. So every smaller values means that that model is doing well. Now, the nice thing about the AIC and the BIC value is that if I have multiple models and then I want to compare them, then I can compare with multiple models. I can pick this particular model, pick its AIC, and compare it with another model using the same AIC. If my outcome is the same, right? If I'm predicting the same thing, then it doesn't matter what the model I'm using is. I can pick a logistic regression. I can pick another type of model as long as that model can also gives me AIC and BIC values and it is predicting the same outcome. I can do a comparison between these different models. And so that is one of the nice things about use of AIC or BIC. Models that are the same, so several logistic regression models, I can compare them, but I can also have maybe a logistic regression that has maybe polynomial components. I can still compare them. I can also use it for linear models. So if I have linear models, remember in linear models, we can also fit linear models. We can fit polynomial regression models. As long as the outcome is the same, it doesn't matter what type of models you are fitting, you can still compare the performance of one particular model versus the other using the AIC, the BIC value, or the -2 log likelihood values. So that is what we want to do here. First of all, we need to fit the model. So here, what I'm doing is that I'm fitting a different model. So I'm fitting another third model. In this third model, I'm only fitting so remember I have model number 2, So here I have, assuming that I have model number 2 and it is age, sex, age group, wind, wealth index, residency, and hypertension. But I have another model which is just age and then the hypertension. That they are the ones that were significant. If we go back and look at our results, this model and this model were the significant models that we had, significant factors that we have. So if I wanted to use AIC or BIC values to determine whether, so should I report this model or should I report this model? All right. Then I can compute their AIC and AIC and BIC values. How do I compare them? AIC, I can pick the first simple linear regression model that we fitted, the second model that we fitted with all of these independent variables, and then the third model, which is this one, the one which has only the significant factors. Then I can compare their AIC values. So if I check all of the models, model 1 is giving me an AIC value of 2293. Model 2 is giving me 2176, and model 3, which has only 2 factors, it's giving me 2169. So if I'm using the AIC to judge which of these 3 models is the best, then it is telling me that model number 3, which is the this particular model, which has only the significant factors, are the ones that I should use. If I also look at their BIC values, again, even the BIC, that model number 3 is coming up as the best model. Now, the disadvantage of using the AIC and this BIC model approaches is that it means that you have to fit all possible models. I have to fit all the different combinations. Okay, if I put this here and this here, if I put this here and this here, I have to put all of them together. Then I would then tell it that, okay, of all the models that I have fitted, which one of them gives me the best AIC value or the best BIC value, which can be a lot of work, all right? But that is one way in which you can decide which model is best for you to use. Okay, so because of that, in R, there has been a package that has been developed called the step AIC function. And this step AIC function, I can tell it that the model, if these are my parameters that I have, fits all the possible models given fits all the possible models using this AIC values to tell me which of them would be the best model. Martin, your hand is up. Please go ahead with your question.
Yes, thank you very much. I just wanted to, the statement that you just mentioned about there's so many models that sometimes we fit. Is there a clear criteria that you would recommend a statistician to use if they are facing such a situation? I know sometimes you have this number of parameters. Some of them you're not, you don't have information from literature whether they have been consistently important from different papers, and then you have such a number of variables. So as you're trying to come up with these different models, trying a model with ABCD and another one without this and another one with that, are there some of the things that you'd recommend that you should look at to reduce on the number of models that you could come up with?
Oh, okay. Yeah, so I would have answered that question at the end of this section. Okay, so let me just finish this and then I'll answer that question and put everything together, everything that we have learned together. Okay, so just allow a few minutes and then you would have your answer. So like I'm mentioning, there are possible combinations of the independent variables that we can plug into our model. Okay, so so each of these models, we can get their AIC values, we can get their BIC values, we can get all other metrics, and then we can just decide. Now we know how to use the metrics. If it is R squares, we want the ones which are higher. If it is based on sensitivity and specificity, we want the ones that are higher. If it is based on AIC and BIC, we want the ones that are lower, etc., etc. So there are so many options that it's available for us. R has a function called step AIC that relies on the metric AIC. There are others. There are other metrics that you can use. You can use the BIC. There are packages that can handle all of these different metrics that are available. And it is very simple. All you need to do is that, first of all, fit the model with everything. Okay, so we have some, there are also packages that does what we call forward selection, backward selection, stepwise selection. This is a stepwise selection criteria where the metric for determining which model is best is based on the AIC. We also have some that is based on the BIC, some that is based on the bias. You can based on the bias of the model, several other metrics that can be used. Because AIC is widely used, I mean, this approach is also very commonly, very popular, and has been shown to also do quite well. So when you use this function, this is what happens. It fits all the, so you fit one big model, put everything into the model, and then it would calculate the AIC for this full model, the model that has everything. R will calculate the AIC. Then it will remove sex, which is the first variable, fits the model, and that model. So first, so in this particular case, it fits the wealth index. Okay, wealth index was the one that it removed, and then fitted the model. And then once it fitted the model, and calculated the AIC. Okay, then it removed sex again and computed the AIC. Okay, it does that, and then till the end. Then at the end of the day, it checks which of them do I have to remove so that I still have the smallest AIC value. So which one? So if I look at this, then you see that the wealth index was the one that gave us the is it the lowest AIC? 2172 2174 2176.
It is age.
Okay. And then what? Age is what? No, age is actually bigger. Okay, so I think the one that is placed at the top means that when that one is in the model, when it is not in the model, we get the lowest AIC value. Okay, when we remove the this variable, it is when we remove the wealth index, that is when our model has the lowest AIC value. So it means that we need to remove this from the model. So it removes that from the model and then fits this model again. And then it will repeat the same process. It will compute the AIC value for this, which is the one that you see here. Okay. And then it will remove one of the variable at a time. It will remove sex. It will remove the age group. It will remove this and it will remove that. And then see how the AIC values, which one becomes the AIC, the lowest AIC value. So here it is telling us that it is when we remove sex, that is when the AIC values become what? Very small. And all of this is done automatically for you. So R generates all of this and then gives you what the final model would be. So as long as this AIC value here is still better than this, the model will not stop. So it would continue the process until the AIC value you have here, and then the model that it's finally retained, the AIC values are the same. So I don't, some of the results are not showing. So let me see if I can switch to the R, and then I run the R from there. Okay, so this was the model. here, then I do the step AIC, then I can show it from here. Okay. So you see that it follows so many steps. Okay. So we were at this step. So here it fits this model. And this model, it has this AIC. The AIC value is 2172. Okay. So can we get another model that can give us a better AIC value? It tries again, remove sex from it, remove this, remove that, remove that, remove that. And then it gives us one. Oh, this one, it says that if I remove sex, then the AIC value will drop to 2170. Okay. So then I'll say, then I like that model. So I remove sex from my model. And then I do, I fit the AIC value is this. Can I get a model that will give me a better AIC value than this? Okay, so then let me remove this one, let me remove this one, let me remove this one. After removing, which one gives me the smallest AIC? The AIC after I remove residence comes down to 2169, which is lower than this one. So I continue the process. I go to the last one. So it means that if I remove that, then only this remains. Now, when I do, if I don't remove anything, which is the none, then the AIC value is this. But when I remove all the other ones, the AIC values becomes higher. So that means that I don't have to remove any other, but then I'll pick this model here as my best model. And that is the one that I would pick as my final model. Okay, now to wrap up of all of these things that we have done. When you are a modeler and you are modeling, you have a data that you want to model and determine which is your best model. Our brother asked the question that how do you go about this? So you have to go through these slides from the back. So remember where we started from, fitting the models, deciding, interpreting the models, you know, we came all the way to how do you test the diagnosis and everything. So in the classroom, when we are teaching, we teach according to that, because it tells us that the disadvantage of doing certain things, and then we see how do we improve it. Disadvantage of doing this particular thing, and how do you improve it? So the best way to start approaching modeling is to see this process from the back. So starting this from the back means that if I have a practical problem, I have my data set that I want to analyze, okay? The first thing that I'll do is that I need to identify the independent variables or the factors that I think are relevant for to predict the outcome. So I can use the literature to decide, get a lot of variables, and then put all of them, get all of them, make sure that I have cleaned my data and everything. So I have all this set of variables. Now, this set of variables, there are some group that are the reasons why you are conducting your research. So the exposure variables, these variables, whether they are significant or they are not significant, they are the reason why you are conducting the research. Those variables automatically, no matter how you do your model building, they must be in that model. Age and gender are two variables that even when they are not significant, or even when they are not significant, you have to still have them in the model, because they help you to adjust for the other. They are generally practically known that they are very they are confounders. So their significance or not significance is not a problem of concern. Okay. So what I'll do is that I'll identify all of these sets of variables that I mean, for those ones, automatically they have to be in the model. Okay. Then the other ones that do not have to be in the model, do not necessarily have to be in the model, but I need to know whether they are important or not. I'll have those sets also as well. So this is how I approach modeling. It doesn't mean that that is the best, but that you can also adapt whichever way that you want. So that is what I do. I'll pick those ones that they must be there and the ones that do not have to be there. Then I'll start to build a model I can use the AIC. So like I mentioned, we can start from behind. I can pick different other types of metrics. Decide on AIC, decide on BIC, decide on all other metrics like the CP or DS betas, you know, depending on the type of model that I am doing. Then I will check the performance, the consistency in terms of how all of these metrics are determining which variables should be placed in the model. Okay, so maybe I find that, okay, when I use the metric AIC and BIC, it seems to be giving me the same type of, it seems to be picking the same type of variables as my best model. Okay, so it means that I'll pick those models, and then I'll say that, okay, maybe this one should be the best model. But then you can also have an alternative model. So there should be, all the time, you don't just work with one model. So you also have what is the next best. So according to these metrics, which of the other models is my next best option? Okay, so maybe I have 2 or 3 models that I have selected based on this. Then those ones, I go and now try to fit the models and now start looking at how are they doing in terms of the metrics. How is it performing in terms of my ROC curve? How did this performing in terms of my sensitivity on my specificity? How is it doing well in terms of my recall? Then I'll use those metrics to judge out of those ones, which ones do I think is performing best. Maybe I can use that to reduce my model to maybe 1 or 2. Then I can do my goodness of fit test to see whether those models, that the 2 models that I have finally picked as my best, are they all satisfying the assumptions that I have in my model. So then I'll perform my those diagnosis or residual analysis on those models to be convinced that these models are actually doing well. I'm not violating any assumption, etc. Then once I have done that and I'm satisfied that, okay, now this is the model that I have considered as the best model, then I can go ahead to do my interpretation of the odds ratio and things that we have talked about. So you can see that in terms of practical things, you actually would have to be moving from backwards. So all the things that you find in the textbook that are done later on, you have to start doing that from the back to determine what would be considered as your best model. But people have different ways of doing that, fitting important models, but this is one strategy that you can actually adopt. Pattern on age and gender, that much be there in the model. Johnson, do you want to, your question is not very clear.
Yeah, thank you, Doc. I was trying to say I needed some clarification. You were trying to say that the 2 must be there, whatever they are not statistically significant or not. So I just wanted to get the clarity.
Yes, so I'm saying that most of those factors, especially in terms of reporting, in terms of public health, when you want to report, like you have age ranges like of people, you want to see, you still want to make sure that you adjust because people are different, they have different ages. So maybe the age is not directly related to the outcome, but the other factors that you are testing, you need to adjust for the fact that there are differences in the population. There are people who are younger, there are people who are, so I'm looking at, even though I'm looking at depression, right? But then depression rates amongst children cannot be the same as among adults or, among different age groups. So maybe the data that you have collected may not be showing that there are differences. And so even if you don't see them, these are, epidemiological, known to be factors that you need to add, like, it's always best to adjust for. And I mentioned age and gender as one of the biological factors that it's often advisable that even if they are not significant, still adjust them and leave them in the model as long as they are not, correlated with any of the other factors that you are considering. Okay, so that means that even if they are there, they will not alter the effect size so much, but they can help you to be able to explain that you have actually adjusted for these factors, because they are very known confounders. And so if you don't include them or you remove them in your model, then somebody will raise a question that, yeah, but we know that these are obvious confounders. Why did you leave them from the model? And I just picked the age and gender, but there could be others depending on the kind of research that you are working, where in that case, that particular research have very key confounding variables that you cannot get rid of. So in that case, and that is why I said separate those ones that are important confounders that need to be there. They must be in the model. The other ones that are optional, you can still play around with the model building techniques that you have learned, so that they don't introduce a lot of bias into your model. And then you can come up with a final set of predictors for your model. Okay, so I think that summarizes it. So we are good. We've been able to at least finish the logistic regression, and how to build models. The concepts that we have learned are going to be very similar when we handle the next GLM model, which is the Poisson regression. So we are going to stop here for today, and I look forward to having the section on Poisson regression and how we can go about building this model using R. So at this point, if there are no other questions, then we can bring the class to an end, and then Joel would help us set up maybe 1 or 2 sections to complete the Poisson regression and the other type of models that we want to consider before this section ends. I know it's a very difficult modeling class, but the concepts here, we can always apply them in other contexts. So it's very good that I think it's a time that is well spent. The concepts here, even when you are doing machine learning modeling, you are doing other types of modeling, these concepts are still very important that you can apply. Okay, so if there are no questions, I wish you all the best and see you next time. I think my email should be on the slides. If it is not, then I have to put it there. Okay, I don't have my email here. So my email is xiddi@aphrc.org. All right, no questions. I wish you all the best. See you next time. Bye.
Bye everyone. We'll try to catch up. Bye.
Bye, everyone.